All right. So far, what we have gone through is we have learned about what is a vanishing gradient. And in order to overcome vanishing gradient, we learned about weights initialization. We learned about various activation functions like ELU and so on. We also learned about the batch normalization in order to overcome vanishing or exploding gradient. And in order to, again, in order to further handle the exploding and the vanishing gradients, we learned about gradient clipping. Afterwards, we learned about how do we reuse pre-trained layers, as in the transfer learning. Then, then we started with the next topic called faster optimizers. After this, we learn about regularization, and that will be pretty much. All right. So this is where we are right now. Great. Now, so afterwards, after this session, after these two topics, we are going to start with CNN, the convolutional. Sorry. Okay. So we are going to start with CNN, and then we will continue from there. All right. Now let's continue with our learning of faster optimizers, right? So earlier we learned about something called gradient descent optimizer, right? And gradient descent optimizer is something that we use everywhere, right? We used everywhere, and we also talked about various variations of gradient descent optimizer, like we talked about SGD, the stochastic gradient descent optimizer, and then we also learned about mini batch and so on, right? So those were the added improvements to gradient descent. Now, there were additions to gradient descent optimizer, and these additions are as follows. So we're just going to go over the list, and of course, in the end, we're going to use Adam optimizer, but Adam optimizer is essentially a combination of RMS prop and kind of the it's basically improvement over a combination of momentum optimizer and RMS prop. So these are basically all related, and that's why we would like to go through all of them, right? And that also will make you give you an idea as in why we are as in how the training actually happens, because under the hood, under all of the neural network, it is essentially these gradient descent optimizer which is at the work. This is the main part about main part of the learning, right? While uh, CNN, RNN, they are essentially the rearrangement of the fully connected neural network that we have studied so far. But under the hood, it is the gradient descent optimizer that remains there everywhere. So we must learn about the various optimizations done to gradient descent. All right. Now, the first one is momentum optimizer. I hope we learned last time. So in momentum optimizer, what we did was we instead of instead of again, a quick recap of gradient descent. In gradient descent, what is it that we are trying to do? What is it that we are trying to do? We're trying to find the slope at the current position and in whichever direction the slope is going down, we go in that direction. Now, we don't go in that direction with a fixed step size, like normally humans do, that they go in the direction with a fixed step size. In case of the gradient descent optimizer, we go to the direction where the slope is steep with a bigger step size. The step size is a function of the slope. Bigger the slope, the bigger the step size, right? So that's what we do there. Now, further to that, to make it further faster, what was done was we basically there was an optimization called momentum optimization, whereby your previous slope, the impact of the previous slope was added to the current step. So your current step was a function of your previous step plus plus the current the current slope. So the previous slope and the current slope. That was the basis of your next step size, right? That's the momentum. So basically, it's like you are adding your previous speed is still retained, and further speed is added due to the slope. That's how the momentum looks like. So like the way if you have ball rolling down the slope, the ball doesn't stop and again restart, right? The way in gradient descent, we stop at a point, then measure the slope, then take the next step, and take the next step, and then we move in that direction, right? But in case of momentum, whatever was the previous summation so far of all the slopes, that is what is impacting. Now that one is really faster, as in couple of steps you are at the bottom, right? So 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 basically it will start slowly but quickly pick up the momentum until it eventually reaches the terminal velocity, right? So basically this is what we learned earlier. So we basic here, if you see the momentum optimizer, we are computing the momentum at every point. How? Adding the previous one plus the rate of change of error with the eta. So this is our current momentum, and based on this momentum we are subtracting from theta, right? So instead of only the current slope, the previous slopes are also being used. So this is momentum optimizer, and the advantages of momentum optimizer is that this is extremely fast, and how much to carry the previous momentum is decided by beta, and how much to add the new the impact of the new momentum is a function of the learning rate, right? So this is what the momentum optimizer which we talked last time, and I hope this is clear to everyone. Bintao, James, Pavan, Pratik, Ross. Now, to now the further improvement to the momentum optimization came from Nesterov, and that's a interesting one. So before I move on to that, a question from Bintao is how to choose the value of m and beta, right? So m would initially be 0, right? And m would initially be 0, right? And so initial value of n will be same as the way we do in gradient descent. So it'll be m will be eta multiplied by rate of change of error, the slope of the hill, right? So rate of change of error with respect to theta. So initially this m is going to be 0, and then it'll be computed like this. Then in the next round, when the next step occurs, the previous m will be multiplied by beta, and new error rate will be added to it. So that's how the m is computed. Now, we don't choose the m as such, but we do choose beta. So so typically we generally use the beta as zero point 0.9. That seems to work mostly. If we choose beta at 0, that means it's a classic uh, gradient descent optimizer without any momentum. And if you put 1 here, then it'll be extremely fast, and there are chances that it'll keep on jumping around the down the hill. By the time it has reached the bottom of the hill, it has gained so much momentum that it will go up again, and then after some time it'll go down, and then it'll keep on oscillating. So if you have high values of beta, there's a high chances that it would oscillate. Okay, it would oscillate. So you have to keep beta somewhere between 0 and 1. Okay, and beta, typically people keep it as zero point 0.9. We'll learn more about it as we go ahead. So great. All right, was he able to answer, Pinta? All right, the all right, was he able to answer? M for momentum. Okay, and the beta is the sorry. So the really sorry. So M is essentially, I'll tell you. So M is momentum vector, and beta is momentum hyperparameter. And essentially, if we have, okay, so okay, let me go back. So M actually represents the velocity. We call it velocity, not the momentum vector as such. So though we call it, okay, so though it is m right now, but the way we look at it is the v as in velocity, or we also call it momentum vector, and beta is the one that represents the momentum, because if beta is 0, there is no addition from the previous step. So yeah, so I think, yeah, the a bit of nomenclature differences. So m is for the velocity, or you can say momentum vector, while the beta is the one that is actually adding to the momentum. Okay, so sometimes we just call beta itself as the momentum, that how much we do want to gain the momentum. Okay, so yeah, all right. So the velocity is increasing every time. Velocity is increasing every time, and the hyperparameter beta is essentially the one that is making that happen. And hence, I think that is what is called a momentum. Because momentum, if you think about the physics, the momentum is what is the carryover from previous step. I'm having a momentum, meaning that because of my past speed, I'm having my current speed. Okay, so this one is the momentum. This, I think this whole thing is called momentum. I think the terminologies we will clear later on. Okay, question from Binta is, how do we choose the initial value of m? Initial value of m is 0. Initial value of m is 0. and that's how it goes. So, when we are computing initial value, as in when we are for the first time, let's say we are computing m, so this part will be 0, okay, and only this part would be there. So that'll be exactly the way we do it in gradient descent. All right, great. Now moving ahead, so what we learned was that momentum optimizer is faster than gradient descent, but there are little bit troubles to the momentum optimizer because it it by the time it reaches the down of the hill, at the bottom of the hill, it has gained the momentum and it goes to the other side, and then it takes some time for it to come back, and by the time it has gained the momentum again, and therefore after it reaches the bottom of the hill, it oscillates. Okay, now the the further improvements to optimizer came from Nesterov, and it was an interesting optimizer. So instead of you instead of you taking the step, instead of you computing the slope where you're standing, instead of you computing the step where you're standing, you compute the sorry instead of you computing the slope where you are standing, you look down at, based on your momentum, that if we don't move at all, where will we land up in the next step. We just take a look at that part, and at that position we compute the slope, then it'll be faster. So instead of computing the slope where you're standing, you look down and see that, okay, in because of my momentum, I'm going to reach there in the next step. And at that point of time, what will be my slope? Okay, and you add that slope to the momentum instead of your current slope. Okay, so that's a very interesting um, uh, optimization to the optimization. So so here, would you compute the instead of computing at theta, you compute at theta plus a little bit of the previous momentum. Okay, so that's what is about the Nestro optimization. All right. So if you take a look at this one, all right, you are here, right? You are here. Your if you go with the current slope, this is the next step, right? This is the next step, right? This is your basically your current um, current slope. While the previous one, at this point, you have this much of momentum, this much of velocity or momentum at this point. So either you could just add the speed to this one, okay? All right. Or either you could just add the speed to this one, this speed, the W1. So at the slope, the next step, because of the slope, either you add to this one the current momentum. This is what the typical momentum optimization was, or you compute your slope at this point because of the momentum, and there, whatever is the next step, you use that. So you sum up this one. This one always comes as better one. Okay, this one always comes as better one. And so this is essentially a tiny shift from the momentum optimization. The main difference is, instead of computing the slope at where you're standing, you predict that my next step, by the time we reach the next step, it is going to be my momentum, and at that point you compute your next step, and then that's what you add to your current momentum. All right, so this is so you compute your next step based on the current momentum, and use that to to compute the next step, all right, or improve the current speed. All right, so does it make sense to you? All right, great. So it's like looking into a bit of future rather than your current state. Also, this reduces the oscillation that was happening because of, but see, because when the so the way momentum optimizer would work is that it will start rolling, and by the time it reaches here, it'll go up. But since, let's say, here, it it observed that, okay, the slope is coming down, so increasing too much of increasing it. So here, let's say here, your next step is, say, here, right? So the slope would come down, and therefore it won't move very fast. Instead, it'll move slightly slower, right? So that's a very important optimization. So it basically converged a bit faster than the momentum optimization. All right. So this was Nesterov accelerated gradient, which is an addition to the which is an addition to the the gradient descent. All right. So gradient descent itself was a really big step. If we did not know the slope, if we had no idea about the slope, we could have just increase. We couldn't use, let's say, gradient descent. So we could have just used a fixed step size and then see whether it is decreasing or not. But that could have been insanely slow. So the gradient descent optimization helped us to reach the solution faster. Then momentum optimizer made it further faster by keeping track of the past. The Nestero optimizer, instead of looking at the current location, it looked into the future a bit and computed the next step based on a bit of future. So that's an important part. And next is, so gradient descent optimizer starts quickly. Okay. Now the next one is ADA grad, right? So gradient descent optimizer starts quickly going down the steepest slope, right? Then starts going down, start becoming slower and slower as you are reaching the bottom. It would be nice if the algorithm could detect this early on and correct its direction to point a bit more towards the global optimum. Okay, it'll be nice if the algorithm could detect this early on and correct its direction to point a bit more towards the global optimum. Okay, so so mainly the momentum optimizer, what was it helping in? Since gradient descent was becoming really slow by when the slope becomes kind of horizontal, therefore, it utilized the momentum of the past to reach to the bottom faster. That's what momentum optimizer did. Now, further, the ADA-grad algorithm achieves this. So what ADA-grad did was, it's called adaptive gradient descent. And what it does is it computes the steepest slope. It finds out the the squares or the magnitude of the slope and divides it with the current speed. All right. So here, what it does is, it is essentially adding squaring the gradient descent, squaring the slope. Okay, squaring the slope, whatever is the current value of slope, it will square it, meaning it will always become the square. It will always become positive. Okay, so and it'll keep on adding to the slope. So what it does is the it would it it will start with 0 value. Okay, and then it'll keep on increasing this as is scaling. I think it's called scaling. And we basically square the rate of change of error with respect to theta, and then the next step is, while computing the cost, it subtract here it divides the slope by the square. Okay, which means that out of the, so it's essentially about scaling down. Okay, so it basically scale down the fastest direction so that it doesn't move extremely fast. Initially it'll move a little slower. as the as the slope becomes shallower and shallower, it gains the speed. Okay, so you have two factors to it. One is scaling. Um, here you can see that it is basically summing up the squares of this. So if earlier it was really fast, and later on it became slow, so the rate would be would start slower, and then it'll become faster towards the end. So that's what is happening here. So it's essentially scaling down your rate of speed. Okay. And let me just tell you this. A question from, okay, so yeah, this part, right? This part. This part is square. This is square. It's not second derivative. It's a square of your rate of change. So in every direction, what it does is in every direction, it computes your rate of movement by dividing the squares, like computing the unit vector and then moving in that direction. All right. It's about computing the unit vector. And also the next step here is basically addition of the previous steps. So this value keeps growing further. It's a positive value which keeps growing further. So that's how. All right. So Adagrad did do good job, but it was extremely slow because this value kept on growing, and hence this theta stopped changing after a point of time. All right. So here the epsilon that you see, so it's basically the square of your slope. Okay, for every direction, this is essentially a vector in every dimension, and this is the rate of change in every dimension and squared. So in every dimension it is squared, and then it is divided. Okay, so that's what is happening. And so let me go back and just give you a more theoretical background here. So gradient descent starts quickly down, going down to the steepest slope, then slowly. Uh, so whenever it is flat surface, it becomes slow. It would be nice that if algorithm could detect this early on and correct its direction to point a bit more towards global optimum. So, and the adaptive AdaGrad achieves this by scaling down the gradient vector along the steepest dimension. Okay, so the first it accumulates the square of the gradients into the vector S. It keeps on accumulating the square of gradients, and okay, and then so this is essentially the vector form of this one in every direction. So S is a vector. So if you have n number of dimensions, it'll contain n number of values. And how it's computed, previous n values plus the square in every square of the rate of change of j with respect to each of theta I. This is the square of it. It's a scalar. uh, It's a scalar multiplication. All right, it's you can say element wise multiplication. So if it is a one column array with all the gradients and multiply with the second column, same one, we essentially square of each of them. Okay, so that's how it is. And now the next one is that we, all right, so this is okay. Yeah, it's not a second derivative. All right. If the cost function is steep along the ith dimension, then Si will be larger and larger at every iteration. So if the cost function is steep, basically it normalizes it. It forces it to come down to a particular value. It forces it to slow down. That's what it is doing. And here the the second step is almost identical to gradient, but with a one difference that we are okay. So the gradient vector is scaled down by the factor square root of the scalar here. So in every dimension, so it's an element wise division again. Okay. I'll explain to you. So okay, and the epsilon is to avoid division by zero, so you can safely uh, assume it to be really tiny, so that there is no division by division by zero error in computation. Therefore, epsilon has been added. Now this is element-wise division, meaning every theta I is equal to the initial value of theta I. So in every dimension, this is what is happening. So in every dimension, first of all, we are computing the rate of change with respect to each theta, right? This j theta is an error. This is basically the loss function. It is basically a loss function, which we find we find the slope with respect to each of thetas, right? So there will be this will be computed. If you have n number of features, then or n number of dimensions, there will be n such values. Similarly, there will be n such values, and for each of the dimension, we are computing Si equals to previous value of Si plus the square of rate of change of loss function in every dimension. So this one is a vector containing n number of values. All right, if n is the number of features. Okay. Next is for each of the thetas, right? For each of the thetas in every dimension, we are computing theta. In every dimension, we assume the initial value of thetas, right? We assume the initial value of thetas. And then for every theta, what we are doing is we are saying the next value of theta is equal to the previous value of theta minus eta multiplied by rate of change of the loss function with respect to that particular theta divided by that particular s, right? So you can think of it, if I have to write it down, so let me just put it down in the, okay, let me put it down this way. Okay, so if we have let's say there are two dimensions and we are calling them 0 and 1. So s naught equals to the previous value of s naught plus the and for every of these will be computing, right? We'll be computing the let me just say this j theta naught divided by, so we'll be computing this. So okay, let me put it again. So what was the symbol we were using? Okay, so this is theta naught equals rate of change of j with respect to theta naught. right? At the same time, we'll be doing the same thing for theta 1, okay? So we'll be saying d of j by d theta 1, right? At the same time, we'll be having s1 equals the previous value of s1 plus this is theta naught, and this is theta 1, right? The, and square of this, let's say square of this, whatever value it is, it's a square of this. Okay, since it will be a singular value, like here we are saying the theta is theta naught theta 1, and so it's going to be a single value, whether it could be negative or positive, but this factor will always be positive, right? This next step is in the computation of theta. So we are saying next value of theta naught is going to be theta naught minus eta multiplied by theta naught divided by s naught. Now, since s naught could be 0, so what they have done is instead of just saying square root of s naught, just added one tiny number to it. Okay, so that this never becomes divisible by 0. So here on the other side, we'll have theta 1 equals theta 1 minus eta, and this is okay theta 1 divided by square root of s1. Okay, this is supposed to be s1. Okay, this is s1. Okay, and s1 plus a bit of epsilon, this tiny value. Now, instead of writing the same equation, or instead of writing, typing so much of code, which this is whole, or writing another for loop to do this. So instead of this is essentially written as a single theta. All of these combine. So theta is going to be some value like this. Okay, this is theta naught, theta 1, and theta 2. Okay. So this is what it means by element-wise division. Okay. I'll add this to the slides. Okay. All right. Is it clear to everyone what's going on here? So this s and this theta, all of these are essentially vectors, and so on. So in our so the main reason why we use the vector linear algebra or vector algebra is to avoid calculating these so many variables by using either a for loop or other some complex mechanism. So instead of that, we just use the matrix, or you can say the linear algebra. All right, Balaji, Bintao, James, Pavan, Pratik, and Ross. So even though you would never have to worry about any of these parts in your actual work, but it is important to know what's going on, because otherwise it would look to you like a magic. Okay, so this is AdaGrad. AdaGrad is adaptive grad. It basically keeps on scaling down your the the, the slope. Okay, and so what it controls is it controls that if it is going really fast in a particular direction, if it is going really fast in a particular direction, it basically stops that side, and the one that is in the direction it's going at a normal pace, it slows down that side a little lesser as compared to the faster one. So the algorithm decays the learning rate, but it does so for faster steep dimensions than the dimensions with gentler slopes. Okay, so this is called adaptive. So adaptive grade, instead of, let's say here the slope is more, and instead of going in this way, it goes more like this. Okay, because if there is a slope really fast, if theta 1 is changing really fast, theta 1 is changing really fast, or theta 2 is changing really fast, so instead of going really fast in that direction, we'll go a little slower in that direction. And that's why it it so it might take a bit of more time, but the distance covered will be smaller. Okay, you can say it this way. And so it helps pointing the result updates more directly towards the global optimum. One additional advantage is that it requires much less tuning of the hyperparameter eta. All right. The disadvantage of AdaGrad is that AdaGrad often performs well for simple quadratic problems, but it stops too early when training neural networks, right? The learning rate gets scaled down so much that algorithm ends up stopping entirely even before reaching the global optimum. So even though TensorFlow has AdaGrad optimizer, you should not use it. Okay, it may be efficient for simpler tasks such as linear regression, um, but we should not be using it. As you can see that every time we are dividing the speed by the overall rates of changes so far, therefore it's not a great idea. So AdaGrad was a good way to find the shortest uh, way to the to the towards the optimization, but it was also the slowest. Okay, and this is where the other optimization happen. Okay, so this is where RMS prop comes into play. RMS prop, another algorithm, tries to fix this by accumulating only the gradients from most recent iterations as opposed to all the gradients so far. Okay, so what it does is it multiplies with a fraction, right? Beta here is, let's say, some fraction. So instead of carrying over everything from previous steps, it carries only fraction of it. Okay, and the remaining part is due to the present. So beta is a fraction. So if beta is 50, like zero point 0.5, if beta is 0.5, it'll carry 50% of the previous values plus 50% from the current one. Okay, so this way you can control how much to carry from the previous one. So if beta is 0, then this will behave like this will basically slow it down really fast. If beta is 1, then if beta is 1, then this one this one is essentially is going to be 1, right? It's going to be, if beta is 1, then it's going to be 1s, and initially s is going to be 0, and therefore it's going to be really slow. So okay, all right, so in either cases it would be so if beta is 0, right, then okay, then it's going to be only this factor, the current value only. It'll be only current value. It will not carry over any of the previous value. If beta is 1, then it'll have a huge impact from the previous values and no impact from the current values. Okay, so that's how. Now the right. So so the decay rate beta is what is used in RMS prop. Moving ahead. So except on very simple problem, this optimizer almost always perform much better than Adagrad. It generally performs better than Momentum Optimizer and Nesterov accelerated gradient. In fact, it was preferred optimization before ADAM optimization came around, right? Now, so we talked about normal gradient descent, then we talked about Nesterov, and then we talked about Adagrad, and then talked about RMS prop. Now, the the one the ADAM the ADAM, which stands for adaptive moment estimation, combines the idea of momentum optimizer and RMS prop. On one hand, the momentum optimization was extremely fast, while the Adagrad or RMS prop kind of scaled it down, tried to bring it slower, right? So ADAM optimization combined the two into one so that you get the speed of the momentum and you get the shortest path from the RMS prop. And basically, that's what made it possible. So that's the reason why we are discussing all these points. So just like RMS prop, it keeps track of exponentially decaying average of past squared gradients. So I'll show you this. Okay. Now, now this is so you can see that again the momentum, the next, you can say velocity, or you can say next momentum computed is equal to the previous carryover plus the current value. So on one hand, the velocity, or you can say momentum, I'm actually using the wrong one, so I'll take a look at what people generally call it, but I'm very sure that it is kind of increasing the velocity every time. This is kind of velocity. Theta, if you think of theta as the distance, and you think of this as every step, every 1 second as time. So the velocity v is equal to v naught minus so sorry, distance equals to previous distance plus vt, right? And the time is 1 second, and similarly, so this kind of this resembles the velocity, and the velocity is being carried over every time. Okay, so this is what is momentum. So this is here, on one hand we are having the what we learned as part of momentum optimization, and second is the scaling down, right? The second is this the RMS prop. So we compute m, we compute s, and we further divide it by, because here the a tiny change is here, since initial values of m and s are going to be really small, therefore they're going to be really small, therefore we divide it by this fraction so that it becomes higher, right? And once we have these values, then we compute this. We say so this, whatever we did as part of the momentum optimization, we divide it by square root of s. Okay, so essentially it is a combination of RMS prop and the momentum optimization, or you can say Adagrad combined with the momentum optimization, Ada M. Okay, that's what it is. So adaptive and momentum. Okay, RMS prop is nothing but Adagrad with minor improvements of beta. Okay, so I hope this is clear to everyone. If the previous two steps were clear, the RMS prop and the momentum optimization. So this is ADAM optimization. In this, you accumulate the momentum as well as you accumulate the magnitude of the previous slopes, and you divide the current current velocity with the um, total scale so far, and just like you did, so just like we did earlier, and yeah. So this is ADAM optimization. Moving ahead. So here Okay, so this one is clear to everyone. Okay, so we basically keeps on increasing the velocity by carrying over the previous velocity, and but we can fine tune how much we carry over and how much the current impact be by changing the value of beta. Beta is a fraction. So if we say that let's carry over half of the previous velocity and uh, half of the current one, then we just put beta as zero point 0.5. If we want to carry over most of the previous values, like putting beta 1 as zero point 0.9, then the current rate of change, the impact of current rate of change would be zero point 0.1, right? Next is the step number 3 and 4. Once we have computed S, so S and M, so the next is a little technical. Since S and M, initially both of them will be 0, right? They'll be biased towards 0 at the beginning, right? So these two steps boost the initial values. So if S and M are really tiny in the beginning, this beta is going to pump it up. These dividing by beta 1 transpose. Transpose is basically for making it linear, and so on. So essentially, if you transpose is nothing but basically if you think about the vector algebra, so you'll have to transpose it, and that's how it is. So all we are doing is dividing by beta 1, the value, dividing by 1 minus beta 1, and both, and to make the initial speed really fast, a little faster. Okay, so this is what is going on, and then we, yeah. So both the steps of adaptive as well as the momentum are combined into Adam optimization, and this is what makes it really, really successful algorithm. So this is the one that is going to be used in all of the ones that we're going to use in future. All right. So how do we find a good learning rate? So to finding a good learning rate can be tricky. If we set it too high, training might actually diverge. And if you set it too low, then training will never, will eventually converge to an optimum, but it'll take a long, long time, right? So if eta means the eta that we use is called learning rate. And here, if you see the eta is here, okay. So eta is here, while in the last step, we are multiplying m with eta. If this is really high, then what will happen is, what will happen is theta might go to the other side and then it'll start coming back. So it might not diverge. And sometimes since the steps are becoming bigger every time, the chances are that it would go beyond what we thought. Okay, so if eta is inappropriate, you could end up with a lot of steps and it may not converge so easily. Okay, and or maybe it might diverge. But if eta is too slow, meaning the current impact of the 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 slope is too small, then it will take a long time to come down. So so if you set it slightly too high, it'll make progress very quickly at first, but it'll end up dancing around the optimum and never settle down. And we have to use the um, either of them, but even then, it may take some time to settle. If you have limited computing budget, you may have to interrupt training before it converges properly, yielding a suboptimal solution. All right. So again, this one shows you clearly that if, let's say, on y-axis you have loss, on x-axis you have number of iterations, So if the learning rate is way too high, so when the epoch is increasing, meaning the time is number of iterations is increasing, instead of loss coming down, loss might go up, right? If the if the eta is too small, then as the epoch is going, it's basically coming down kind of linearly. The loss is coming down linearly, right? If eta is too high, if eta is too high, right? Eta is high, as in right, not lesser than this one, but it's higher. So then it might come down fast initially, but then it would kind of become static. If eta is just right, then here it would basically come down faster and would keep on growing and reduce faster. Okay, so basically we may be able to find a fairly good learning rate, but training your network several times during just a few epochs using various learning rates and comparing the learning curves. All right, so one might have to try out multiple values of eta. So the ideal, so I'll talk about what actually we do. Let me just go through this. So the ideal learning rate will learn quickly and converge to a good solution. That's the best learning rate. So if we have a good learning rate, we should converge quickly and reach to a good solution. So we can do better with a constant learning rate. We can start with high learning rate and then reduce it once it stops making fast progress. Okay, so if we start with a higher learning rate and then these are called essentially the learning schedules. Okay, the learning schedule is what we're talking about right now. So learning, there are many ways to do it. There are many ways to handle the learning rate, many ways to optimize learning rate. We had already discussed briefly earlier that in the learning schedules, what we could do is we could have higher rate of eta in the beginning, and then we can reduce it. Okay, then we can reduce. So as we are right, as we are going ahead with the training, we could basically start decreasing eta. That is one strategy. And let me just discuss the common strategies. So one is piecewise constant learning rate. Say, for example, we start with zero point 0.1 in the beginning, and then after 50 epochs, we bring it down to 0.0001, right? So it can work well, but it is too much of manual fiddling. And instead, we would like to have more of a programmatic one. Okay. So second one is, the second strategy is that measure the validation error every n steps, just like for early stopping, and reduce the learning rate by a factor of lambda, and when the error stops dropping. Okay. So exactly the one which we are doing in a discrete way, we have represented it like this. So we kind of divide it by 10. We kind of divide it by 10 based on number of steps. Okay. So this works great, but requires tuning of both initial value and number of steps. And the other one is called power scheduling, which is similar to the previous step. Okay, and here essentially what we are doing is after uh, i- after time t, we are dividing eta. Okay, so we basically keep on reducing eta as time progresses. All right, so these are all learning schedules. Learning schedules, what we generally do is we start with higher learning rate, and then we go back to the smaller one. Keep on decreasing the learning rate. All right. So basically, this is how we could control the learning schedules here. So we could define exponential decay, the previous one. So the, this is the exponential decay. Every n number of steps, every step, it is decreasing it by slightly. So at every step, the eta is decreasing, and So what we do is we basically define decay steps, decay rate, global step, and then we compute the exponential decay, and then uh, feed this learning rate to our momentum optimizer. And every time momentum optimizer computes the loss or compute optimizes the loss, what it does is it uses this learning rate instead of the fixed value. And every time this is going to get computed, it is going to compute the decay, and therefore learning rate is going to slow down every time. Also notice the global step, we have defined it as a variable, and global step we are defining as a variable here. So while we are asking optimizer to minimize, we are telling that this global step is we are feeding from outside. Initial value will feed it at 0, and then it'll keep on increasing. Okay. So all right. So basically the main idea here is that we are decreasing the learning rate. Let it fall fast, and then again let it stabilize instead of diverge. So that's what we are doing. All right. The important part to understand is that in the case of Adam, in case of if we are using the Adam, we don't need any of the learning schedule. It actually works well without any learning schedule. The standard 0.001 eta works well, so you actually don't need any of the learning schedules. All right. So but we are going through it because we should know how to deal with the learning schedules. Okay. All right. A question from Binta is, what is R? Okay, so R is, yeah, I'll go back. So probably, uh, okay. So here all we are trying to do is either we decrease the eta manually, or we automatically do it every step. To do it every step, either we use performance scheduling or you use the exponential. Performance one basically does it every n number of steps, and exponential scheduling continuously the drops down the eta. And further, the power scheduling is just a slight more tweak to this one. Okay, and here you see T by R. Okay, so R is one of the parameters. So as you can see, the learning rate will drop by a factor of 10 of every R steps. Okay, R is total number of steps, and T is the sorry. So every R number of steps, we want to drop the learning rate. That's what we are doing. Okay. So if the t is the current time, and every r number of steps, r is kind of a hyperparameter, and so let's say current time is 100, right? Current time is 100, and we are dividing 100 by let's say 10, so it'll be 10. Okay, and so on. So every time eta is divided by 10, then again as the time progresses, eta will be divided by a bigger value, and so on. So c as well as r are both hyperparameters here, just to ensure that every so the total number of so the value here is basically divided by eta, but by a fraction, not complete. So how should I say it again? Let me rephrase what I'm trying to say. So if you take a look at this one, let's say time is t is 10, and r is, let's say, again 10. Now eta will be divided initially. Eta will be divided initially with a bigger value, as in this value will be small, so this it will be 1. So initially the eta will remain as such, and then it will start decreasing as the time progresses further. it'll be bigger value. This will be bigger value, and therefore the eta remaining would be smaller. Okay, so this is basically the exponential scheduling. Sorry, this is basically the power scheduling. Exponential scheduling increases the eta exponentially. Okay, increases the eta or decreases the eta exponentially. Okay, which is not very great. So exponential scheduling does it exponentially decreases the learning rate, while this one doesn't decrease it exponentially. All right. So this is what we call it learning schedules, and we could create our own learning schedule in this way. Here we are using the exponential decay, and we're passing it the various parameter like initial learning rate, the global steps, decaying steps, and so on. All right. Now, after setting the hyperparameters, so let's just go through this code. After setting the hyperparameter values, we create a non-trainable step, global step at 0 to keep track of the current training iteration. Then we can define an exponential decaying learning rate with eta equals zero point 0.1 and r equals 10,000 using TensorFlow's exponential decay. So r could be the decaying step. This is r, which is 10,000, and the decaying rate is 1 by 10. All right. So okay. So this, since we are passing the global step variable, it'll take care of incrementing it every step. All right. So global step equals the variable that we're passing. So this function optimizer.minimize takes care of increasing the global step every time, right? So the T is what global step is. T is what global step is, and initial learning rate we have to give. The global step is T. Decaying step is the R, and decaying rate is this, which is C. Okay, C. All right. So, and that's how we control it. So that's how we. So the thing that we are trying to do is, okay, the thing that we are trying to do it. We start with good. We start with a good learning rate, meaning we want to increase or decrease the theta really fast initially. But as it settle down, we want to, instead of jumping to the other side, we want to bring it down, bring it back, and that's why we are decreasing. We don't want it to diverge once it has gone to the global minimum or local minimum. We don't want to diverge it. Therefore, we are bringing down the eta. We are bringing down the learning rate. So there are multiple ways. One is periodic one, other is exponential one. Next one is the power one. Okay, so we can implement either of them, and by using the global the by using the global step, we could actually implement either of the three. All right. So the important part is here. Since AdaGrad, RMS prop, and ADAM optimization automatically reduce the learning rate during training. So if you remember, RMS prop was actually dropping the learning rate. Instead of having the fixed learning rate, it was dividing it by the total change that we are doing. The more number of steps we take, the S was being increased, and therefore eta, the learning rate was essentially coming down, right? So we don't need extra learning schedule if we are using adaptive, RMS, or ADAM. Okay, so for other optimization algorithm, if you're using, say, plain momentum optimization, not using ADA or ADAM or RMS, if we are just using the standard momentum optimization, then we can think of using the exponential decay. All right, and that will basically stop it from diverging. Okay. So the conclusion is that we should always use Adam optimization. We really don't have to know about internals. Simply replace gradient descent optimizer with Adam optimizer. And with this small change, training will be several times faster and will converge sooner. All right. A question from Ida is, what are the parameters corresponding to the codes of R and T? Right. So what are the parameters corresponding to the which one? Okay, this one, right? So here, so this is R, this is the power one, this C, okay, and right, this is the initial rate, eta naught, and this is the global step, which is T, and so on, right? Decaying rate, I think, yeah, this is R, okay, and this one, decaying rate, 1 by 10, most likely it is C, okay. All right, so this is what was conclusion. And now, another important part about any of the training, whether we learned normal training algorithms or we learned about, say, um, decision trees or any of the variations of decision trees like ensembles. So it's all about controlling overfitting and underfitting, right? So the same is true in case of the neural network as well. Neural network as well. So how to avoid overfitting through regularization? Let's understand it. So with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. That's what John von Neumann, the father of modern computing, said, right? And and what it means is that if you basically fine tune even the 4 parameters, you can actually do huge tasks and so on, right? And but in case of neural networks, we are talking about thousands of parameters, or sometimes we're talking about millions of parameters. And with so many parameters, we have huge amount of freedom. We have huge amount of freedom, right? If you just multiply 1 million parameters, it is going to be a huge values, right? So with so many parameters, right, we have a huge amount of freedom, and we can fit complex models, complex data sets, and therefore there are chances of overfitting. There are chances of overfitting. It could start memorizing the data sets when you have so many parameters. All right. So how do we avoid the regularizations? Okay. How do we avoid overfitting using the regularization? All right. So when we have millions of parameters, all the weights and biases at every step, the chances of overfitting is too high. Okay. And the more number of layers you have, the more chance of overfitting you will be having. Okay. So it's very important to learn regularization. And there is a difference between normal regularization and here there are newer techniques which are really, really good one, and which is something which we never thought that would work. Okay. So do you have any questions before we move on? Anybody? Balaji, Bintao, James, Shahrukh, Pawan, Pratik, and Ross. Should we move on or? Okay, let's move on. All right, Binda, I hope the question I was able to answer your previous questions. What are the parameters corresponding to codes for R and T? Okay, T was the global step and R was the decaying steps. Okay, why don't we try scripts? Okay, let's just give it a shot. And all right, yeah, good idea. So let's just take a look at, yeah, let me just go through the ones that we were talking about. Okay, so where are we? Yeah, it's a good idea. Let's just give it a try. All right. So where are we? Or should I just pull the code? So let me go to my ML folder and say git pull. Great. So yeah, there's no change as such. And we have talked about this, but we'll just go down from here. Okay. This one is anyway required. All right. Now let's go down and okay, so we have already talked about these parts. We've already done this. All right. Then this is already done. Okay. All right. So yeah, I think from here, let's start. So if we have to use the, okay, let me just initiate the rest of the logic. So here we're creating, this one is the previous step, not this one. Okay. So this is also done. So the way we generally use the momentum optimizer is like this, just initiate this. Okay. And where did we define the learning rates? Okay. Just go over this. No, have to go up. Yeah. So actually, these things we should have defined it here. Okay. Okay. Write the initialize. Okay. Imports and other variables needed. Okay. So all right. So here, all right. Now, so this is how we can use the momentum optimizer. This is how we can use the nested row acceleration by use nested row. Then this is how we could use Adagrad. This is how we could use the RMS prop. Okay, so, and this is how we could simply use Adam Optimizer. All right. Then further, we talked about the learning schedules. And in the learning schedules, this one was here. We defined, okay, so yeah, so we defined X, we defined Y, then we defined hidden layer 1 and 2, okay, and logic. So these are three layers we defined. Then we defined the loss function uh, after defining the cross entropy. And then we computed here, we defined the accuracy. And then we, okay, then we, here, the training part, we basically, here, this is where we are defining the optimizer, okay? This is where we're defining the optimizer. So here, we could change the optimizer either to momentum or to adaptive grade. And the learning rate here we are using is exponential. All right. So once we have created these steps, the graph, then we can start to train it. We can start to train it. Okay. MNIST is what we need to import. Okay. All right. So it'll be, what will be? Yeah. Here. This part, I'll just take it from here and keep it down. Yeah. All right. So now it should work fine. All right. So I hope this is clear. So we're defining global step. This is just another variable. Okay. And learning rate is a function, is basically an exponential decay function of the initial learning rate, global step, and the decaying step and decaying rate. Okay, that's what we are doing. And once we are done with that, we are running it. All right. So it's doing, all right, the standard MNIST one. So if you are using adaptive grad, you don't need to do anything of this sort. Okay. All right. Let me just, in the meantime, I'll try to write this part. Okay. If you're using the adaptive mechanisms, then you don't need any of this. So I'll just take this, all right, and use that. All right, so this optimizer here would be, this is good enough. And let's just use the fixed learning rate. Okay. And we're not going to use the global step. Okay. So here we are just iterating 5 times. All right. So here we're saying, okay, Let me just see what error are we facing. This is correct. Yeah. Are we using any of it from before? So we are saying this is good, this is good, and okay, we are getting the next batch, then we are running the session on the top. This one, then we are computing these. All right. Yeah, we need to initialize it again. Good. Okay. Yeah, we just need to initialize. I think we just need to reset a graph. That's all. Okay. All right. So you can see that if we are just increasing this to say 20 steps, and then we should get good enough results. All right. You want me to commit it? Or we could actually do here. I've actually used these previous steps. Okay. These previous steps is what I've used. I could just copy paste it below as such. Okay. I could just copy paste it below. All right. All right. Good. So you can see that it's working fine, and it's not bouncing around too much. Even if we increase the number of epochs, it'll work fine. All right. You can try switching this to momentum. Try changing this line from above, and then observe how it goes. Okay. Observe how it goes. All right. So I hope this is clear to everyone. Yeah. One question is there's one question. When do we use run and when we use eval? In case of run, let me just give you a correct example here. Okay. Right. So, right, right. So when we are using eval, we get a return value. That's the important part. And the run does not give you the return value. Okay. Run does not give you the return value. So that's the difference between run and the eval. All right. They both do the same thing. They both do the same thing. If you, let's say, okay. So if you want to take a look at it, let's say accuracy.eval, we could just say question mark. All right. So, right. Okay. So basically evaluates this tensor in a session. That's all. All right. So it basically evaluates a value and returns you a value. Okay. And the session dot run, if you take a look, where is the session dot run? Okay. I could just say something of this sort, right? So it basically, the run actually evaluates the entire tensor just like session, and it does. Okay. So basically the eval and run does the similar things. Okay. The eval returns you the value, while this one does not. Okay. So I hope this is clear. This I'm going to delete. All right. Should we move ahead? Do you want me to commit it? Diff. Okay. All right. Done. So let's continue. All right. So is everybody able to execute it? I have pushed the code. You can pull it and try it. In case you are facing error, you can just do checkout, and that'll be good. Okay, let's take a break. Yeah, makes sense. So question from Binta is how to avoid overfitting and underfitting, right? So that's what we're going to discuss now. So avoiding, in case of neural network, something that we are not going to discuss is underfitting, but let me just give you a brief. So in case of neural nets, the chances of underfitting is also there. It's there. Like you have less number of input neurons than, or you have less number of, say, middle layers and so on. So underfitting is definitely there. Okay. And to avoid underfitting, we generally come up with like the reason why we have activation function, for example, is to bring in nonlinearity so that we don't try to fit in straight line, right? Therefore, those kind of tweaks are there, right? So underfitting and overfitting are essential or kind of the we start from while we are doing machine learning, we start from avoiding the underfitting, right? Or you can say we start from the point that where our model is underfitting, and then when we overcome that, we end up in overfitting, and then we overcome the overfitting, right? So overfitting could be overcome by various techniques, but underfitting is always like a research area. The reason, like our overall accuracy of say it's actually hard to say this. So if one model is performing better than other, so and other model is not performing better. All right, let me put it this way. Okay, let me restate what I'm saying. So underfitting is all about underfitting is when we are trying to fit a very simple model into a complex one. That's an extreme example of underfitting. But if you take a look, the earlier earlier, say the models like linear, the models we used earlier on MNIST, they were giving us an accuracy of 91% or 92, right? So they were underfitting from the perspective of neural nets, right? So they were underfitting, and on the other hand, we have the overfitting part. So let's continue. Now, how do we, quick question is, how do we differentiate between underfitting and overfitting? Overfitting is when, overfitting can be easily detected when your algorithm is performing great if tested on the same data as it was trained on. Okay, your algorithm is considered to be overfitting when it's giving you great performance when tested on the same data as it was trained on. Okay, and it's giving it, but it is giving bad results when it is tested on the data that it has not seen so far. So overfitting overfitting is like memorizing, and underfitting is like not studying for exam and trying to solve everything based on the chapter one, right? So underfitting is like going to an exam and only memorizing two cities. Uh, 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 let's say there is a question in the exam saying, "Hey, write all the cities, or write the names of all the cities in a particular country." Now, just memorizing two cities and repeating them over and over is actually underfitting. Similarly, going to an exam and there is a question that multiply two numbers and trying to just answer it with addition and saying that addition looks like multiplication is underfitting. All right. While if right, while memorizing the whole maths book and going to an exam and just if you have seen the question before in the you're like memorizing the entire maths book, all the sums, right, and answering those sums really well based on the same book. But the moment you see a question which is not there in the book, you fail. All right, so that's overfitting. So all right, I hope I'm able to differentiate between the overfitting and underfitting. Now, point from Ross is maybe that's why some of the neural net superstars get millions of dollars. That's right. That's right. Right. A question from Binda is, can I say overfitting is the use of complex mode for simple case? Right. Right. So overfitting is memorizing the entire data. That's more like it. Okay. And yes, generally that happens when we are trying to use really complex models for simple cases. In that case, we are kind of thinking that even if the data is having error, we are trying to think that there is some correlation, right? So great, great. Now, so neural nets are very much prone to prone to the prone to the overfitting. So in this section, we'll go through some of the most popular regularization techniques. We'll start with early stopping, then we'll talk about L1, L2, and then we'll talk about the most important one called dropout. Okay, and so on. So the first one is early stopping. This we have studied earlier also. So here is a very interesting graph. So let me just walk you through this graph. All right. So this root mean square error is on y-axis. This is the error, right? Error in the basically this is what we are trying to minimize, right? And this is number of iterations or epoch. So as we are increasing the number of iterations or epoch, what's happening is the error is coming down, right? We are learning. At this point, we are learning. We are creating the model, we are learning, and the error is reducing, right? the thetas are decreasing, thetas are changing, such that it's in the direction of the gradient descent. So based on the gradient descent, the thetas are changing, and hence we are learning. So here, let's take a look at this graph now. And here there are two data sets. So we are trying the same algorithm. We did 100 iterations, let's say here. We did 100 iterations. After 100 iterations, we checked the error in the training set, as in the same data on which we trained. And we checked the model on the validation set, the data that it has not seen. So as the epoch is increasing, the error is coming down, right? Both errors are coming down. So the training set, the error is continuously coming down. But after a point of time, you will see, after a point of time, the validation error starts increasing. Instead of decreasing, the error starts increasing. While the training set, the error is continuously dropping. So at, say, iteration 500, you can see the validation, the error on the validation set or test set or the data that we have not seen, the error in the unseen data is growing up. There's a huge difference, you can see. While the training set, the error is going down. So at this point of time, you can say that there is overfitting. The overfitting started here. Overfitting started here. All right. So here it's performing bad in the exam. It has started performing bad in the exam, and it has started performing great on the same textbook from which it studied. So here the memorization has started happening. All right. All right. So a question from Binta is, have you ever heard about R square and what's the difference between it and RMSE? So we generally use two words. One is MSE, mean squared error. Other is root mean squared error. Mean squared error is just square of all the errors and summation of all that. And root mean square is square root of the mean square error. I hope that's what you meant. All right. So you can see, I hope this diagram is clear to all of us. So in this case, what has happened is, as number of iterations are passing, as you are studying more and more for exam, and you're just memorizing everything again and again, and you're not checking yourself against the questions that are not that are not there in the book, you end up memorizing. Okay, so this is what has started happening here. Okay, so this is so the first way of solving it is, the moment, this is called early stopping, the moment the error on validation set is going up, you stop. The moment you observe that the error on validation set, instead of coming down, you just stop there, where the moment you observe that error is going up. This is called early stopping. This is called early stopping. All right. So you stop training as soon as the validation error reaches a minimum. This is called early stopping. And right. Okay. Now, the other way, this is like the easiest one to handle. Right. It stops at the minimum error. Okay. So what you observe is, you keep on, what you do is you start moving ahead with the mean square error. And if consecutively you observe that the error is increasing, you stop. Okay, you stop. And so far, whatever minimum error you have observed, you keep that as you save that state. All right. You keep on saving the state every time you encounter a minimum error, and in case the error is not going down and increasing, you stop. Okay. This is based on the validation. The error is computed based on the validation data set, not the training alone. All right. Now the second technique is L1 and L2 regularization. We studied it earlier. What we do is instead of alone minimizing the loss, we also force the weights to be to be we force the loss function to have minimum weights. Okay, that's what we do. And the minimum variation, you can say minimum amount of variation the weight should have. Okay, and we force that by putting L1 and L2 regularization. All right, so we basically need to do, all we need to do is in the cost function or the loss function, we just add these terms called L1 or L2. All right, let's take a look at example of L1. All right, so let's say we have just one hidden layer with weights W1 and the output layers with the weight W2, right? And then we can apply L1 regularization like this. Okay, so you can see here we are saying base loss is here, this is good, this is entropy, standard entropy, cross entropy, and then we are saying this is regularized losses. Regularized losses is sum of all the weights plus the sum of the squares of, sorry, okay, here the L1 means we don't square it, we just compute the absolute of the weight. So W1's absolute summation of that, and W2's absolute summation of that. So what we did was found the summation of all the weights and then added the base and the regularized losses together. Okay, maybe we can put one scale. Remember lambda, we will multiply with the regularized losses with a scale. All right, so what's happening here is, to the base loss, ideally we were only supposed to optimize or minimize these losses, right? We were supposed to minimize using an optimizer, supposed to minimize this. But we also, here what we are doing is we are finding the absolute weights, summation of all the weights and summation of all the, say, biases. So let's say all we do is we just compute the loss based on the absolute or magnitude of the weights. Why? This will force the overall error to be low. Now that can be lower by either reducing the actual loss or by reducing both the actual loss as well as the regularized loss. If you start increasing weights in either direction, whether negative or positive, the loss will start increasing, and therefore this will keep both the variations in the weights as well as the loss in check. Okay, in check. So this is what the core idea behind the regularization is. This is L1. L1 is basically absolute, while the L2 means we just square these values. Okay, so let's take a look at the example in the notebook. So here we are defining X, Y, then we are creating one dense layer, then we are creating another layer. Okay, this is the output layer. And okay, all right. So the cost function and the loss functions are generally the same thing. We just use different words for it. Okay. So here we defined our network, and then we created this. We created the graph or node in the graph which computes the loss. Okay, so how are we computing? First, we created the cross entropy, then we computed the actual loss. This is what we used earlier, but now we have computed one more factor called regularized losses, and loss is nothing but summation of both the second factor multiplied with a coefficient. Okay, instead of the actual one, we just multiply it with some scale. Here it's 0.001. All right, the rest is as usual. Okay, so this is how we start from here. Okay, all right. How about a performance function? Accuracy function, this is an accuracy function. So we are computing the accuracy uh, after the actual work. Okay, so on one hand, the on one hand the session is running the optimizer in order to minimize these losses, in order to minimize the losses, right? On the other hand, we are just printing the accuracy. So, so on the one hand, the model is being trained. On the other hand, we are printing the accuracy of the model. All right. So we have, what we have done is we have regularized our neural net. Okay. This is the first easiest one to do. Okay. This one, yeah, this one is using, yeah, this one is using L1 only. Okay. All right, this is not required. All right. On the similar note, if we want to apply the regularization, just like the way, uh, if we want to apply regularization on two layers, so what we have to do is we will have to, right? We will have to compute or find all the nodes having the losses. So I'll show you this. I think this is covered here. Right. So I'll talk about it. So, okay, so what we did was we computed the L1 losses, and instead of optimizing the base loss, we optimized the summation of base loss plus a scaled version of the summation of the absolute values of all the weights. Okay, that's what we did. So we not only minimized the error, we also minimized the weights. All right, we also minimize the absolute values of the weights. All right, that's called regularization. So in TensorFlow, we can pass a regularization function to tf.layers.dense function, and then instead of we creating the way we did earlier, we are just using this regularizer, because you might have multiple layers, and every time you have to create the loss function, you will have to consider that regularizers. So instead of that, the the function called dense, the function called dense is having a method called regularizer, right? So here we could just pass the argument. I'm sorry, let me just rephrase what I just said. So so the dense function of the TensorFlow has one of the arguments called kernel regularizer. We could just pass any regularizer to it, and it would basically apply that one, apply that one at every point. Okay, so and right, So at any point wherever you want to, want to, okay, let me just put it again. All right, let me just go over again. All right, so the standard L1 or L2 regularizer, what they do is they take the weights, compute the absolute, or L1, what L1 does is compute the absolute, add it to the loss function, and then we minimize the loss function, right? In case of L2, we square each of the weights and sum all those weights, and then add that to the loss function, and then we minimize the loss function. And of course, while adding that to the loss function, adding the weights to the loss function, we multiply that with the coefficient. Okay, we multiply that with the coefficient, and that's what is the regularization about. Now, so the first way was that we computed the losses by ourselves, right? Second one is just by adding one more layer. Okay, just after um, so instead of using the base function of base function of computing the dense layer, right, we created our own function here, and everywhere we added one more attribute. Okay, so that's another we can. So in TensorFlow, we can pass a regularization function to tf.layers.dense and by the name of kernel underscore regularizer. All right. So yes, actually it passes a regularization function, activation function. Yes, that's right. All it does is every time you call my dense layer here, it's going to call this function tf.layers.dense along with these all previously defined arguments plus these three more arguments. Okay, so this function called dense, tf.layer.dense, it's going to be called with first argument this, second argument this, and third argument this, fourth is this, fifth is this. So all these arguments will be going to be added while calling the dense function. So that's what partial function does, and that's what is happening here. So instead of using the vanilla without the kernel regularizer, we are passing the kernel regularizer by ourselves. Okay, so this is how we are computing this is how we are regularizing it. All right, now this code does create a neural network with two hidden layer and one output layer. It also creates the graph to compute L1 regularization loss corresponding to each layer's weight. So TensorFlow automatically adds these nodes to a special collection containing all of the regularization losses. Okay, so here, whatever we are doing, this is same as the previous screen. Now, here it's going to add one more node corresponding to the regularized losses. Okay, now the overall loss is summation of all of the losses. Okay, overall loss is summation of all the losses plus regularized losses. And how did we find out? How did we find out regularized losses? By using this function to manipulate or iterate over the graph. tf.getCollection, and the name of the graph is regularization losses. So this key, if you search, we're basically asking the graph to give us a collection of all the losses here. And then we are adding these losses to our base loss, and that's all. And we are using an add n function, meaning add these nodes to our base loss. Okay, so this is called regularized losses. So these parts are called regularized losses. All right, let me go back. What's going on here? At every hidden layer, right? What is every hidden layer or every layer, you can say? At every layer, there are going to be weights and biases, right? W1, W2, W3, B1, B2, B3, and so on. So there are going to be weights and biases at every hidden layer, right? So we'll have to find out while we are, so for the whole neural network, we'll have a single loss function, right? We'll have single loss function while we'll have loss, while we have weights at every layer. So what we need to do is we need to get all the weights in the neural net and then square them and sum them to the final loss and then minimize that loss. That's what is happening here. So first of all, we added one more node here by telling TensorFlow that hey, we are using kernel regularizer, and then we're then extracting all the weights or extracting all the losses from the graph. This is what this is what it is. So when we say kernel regularizer equals this, what it is going to do is it is going to compute the regularized losses at every node. This is what TensorFlow does for us. And then finally we are computing the regularized losses. We are computing the regularized, extracting all the nodes with the key called regularized losses, and then we are summing it all up and then optimizing this loss. Okay, so I hope that you got the idea. So the summation of all the summation of all the weights at every layer is called regularized loss. So it is extracting at every point whatever is the regularized loss is, and then we are adding it to the final value. Okay, so I hope it is clear. Yes, is loss equivalent to error? That's correct. Okay, all right. So basically, this is what's happening. This piece of code is telling TensorFlow to enable the kernel regularizer, that to L1. And then when we are using kernel regularizer, so whatever is the regularized loss, it automatically, TensorFlow automatically creates the node with this particular name. You're extracting all the regularized losses from the graph and then adding it all. All right, so let's take a look. So this is what we are doing here. Okay, let me go up. Okay. So here you can see we have defined a partial function. Partial function basically makes it easy to define a function and then call it once. If a function is having common parameters again and again, we're calling it, you could always define a partial function. Okay. Now let me just reset the graph again. All right. Now here, once we have defined our layers, then we are defining our loss function here by using the base loss function based on entropy, cross entropy, and then using the regularized losses. This is where these are the three lines different. Okay, generally we were just minimizing this loss, right? Using an optimizer, we were minimizing this loss. Now we have added this term as well. Okay, then we can run it. The rest of it remains same. Question is, what's the difference between L1 and L2? In L1, we find the absolute value of weights. In L2, we square it. We square the weights. Okay. All right. If you want me to do this, I could just walk you through this. Okay. So let me just explain to you in case it's not clear. Let's say you have two neurons and you have, say, one hidden layer, right? So let's say this one is one, and Okay, let me just avoid. Oh, okay. So let's say this is one weight, this is another weight, this is another weight, this is another weight, right? And then there are output and so on, correct? So the loss function is going to be whatever is the error. Let's say we are comparing here with the actual. This is yi. Uh, so this is y predictor, this is actual. And we are also comparing here. So one is that we subtract these two values. That's the actual loss, sigma of something of this sort in case of regression. Okay. Plus we are saying sigma of, so we are saying absolute value of W1, W2 plus W3 and W4, and then we are putting this. So this is something that we always minimized, right? This is an extra term. This is an extra term. Okay. In case of L1, this is modulus. In case of L2, this is just squared. Okay, this is just squared. Okay, so that's what is going on. Okay, is this clear to all? Rest of the logic remains same. The only thing which we have changed here is number one, we have enabled here the kernel regularizer. Okay, and then we have computed we have changed the loss function. All right, and yeah, and then we are evaluating in the usual way. We are minimizing this loss. Okay, we are just minimizing this loss, and then we are running it as usual. Great. So this was a L1 regularizer. It's not a big deal, so we could just use L2 in the same way. Okay. Now, so L1 did good, but L1 or L2 did good as this, just like linear regression or any other regression technique we used in past. But that wasn't great enough. That wasn't great enough, and that was not right. That was not yielding great results in case of a neural net. That's where the technique called dropout came in. So dropout is the most popular technique for regularizing our deep neural network. To avoid deep neural network overfitting, we need to use dropout. It was proposed by G.E. Hinton in 2012. Even the state-of-art neural network got 1 to 2% of accuracy boost simply by adding dropout. 1 to 2% accuracy may not sound like a lot, but when the model has 95% accuracy, then 2% accuracy boost means dropping the error rate by 40%. Okay, so basically, if let's say you already have a model with 95% accuracy, if you just increase the accuracy by even 1%, that's huge. Okay, so if you increase it by 3%, 2%, that is like error going down from 5 to 3%. Okay, if you are just increasing 2%. So 1 to 2% accuracy boost is great when it comes to the machine learning. Okay. All right. So a question from Binta is, sometimes we use null for some parameter, none for other. What's the difference? So none is the default one from the Python, but when we are calling some libraries, they might expect something as null. That's why we generally pass null sometimes. Okay. The default is none, N-O-N-E, right? That's a usual one with Python. Okay, okay. Now moving ahead. So basically, dropout was a great algorithm. Now it's an interesting one, and it's very sounds very strange in first go. At every step, what we do is at every step, including the input neuron but excluding the output neuron, we keep a probability of being temporarily thrown away. Okay, so out of the whole neural network, what we do is, as part of this regularization called dropout, what we do is we drop out or we ignore some of the neurons completely, and that too randomly. Okay, at every point we just do a coin toss and drop out the particular neuron. So a particular set of neuron. So instead of cherry picking and removing them from layers, what we do is, before the neuron is being used, we just do a coin toss whether to use it or not use it, and that's all. So basically, the certain percentage of neurons will be entirely dropped out. Okay, so that might sound strange, but it does actually work. It may be on a particular epoch we drop out some neurons, and on the other we drop out some other, and that's how after a couple of iterations or after few iterations it starts giving results. Okay, so the hyperparameter p is called dropout rate, and it's typically 50%, meaning half of the neural network is actually practically dead. Okay, so let's take an example. How does it work? So in this technique, what we do is, while we are doing the backpropagation and computing the losses and minimizing it, at every step, we just drop out, say, 50% of neurons. We don't use them at all. Okay, that way, that way, it regularizes and it yields really good results. Okay, so let's take an example. Imagine there was a weird company. There was a very strange company in which employees were told to toss a coin, and if it is head, they should come to the office. If it's tail, they should not come to the office. So every morning, the employees toss the coin, and then based on the coin toss, they decide to go to the office. Do you think this company will be more efficient or less efficient? Anybody? There's no right answer because nobody has done it. Okay. Pawan says employees will be happy. All right. A point for James is how many workers were already not showing up due to illness, etc. So yeah, so they were actually the yeah. So in case of our example, we are assuming that all the workers are healthy and all of them show up. But what we have done is we have just tell them that every morning you have to just to do a coin toss, and in case it comes head, only then you come to office. If it is tails, don't come. Okay. All right. All right. Perhaps it would. Who knows? Nobody has actually tried. All right. So we don't. Nobody has an answer, but maybe the company might work better. Okay. We just have to do the validation testing or cross-fold testing or some kind of testing on the company.
Very good question, Vinda. Vinda's question is, will they get pay if they do not work by tossing a coin? As per the neural net example, if you take the analogy, uh, while the if you think of every employee like a neuron which takes input and gives an output, right? And the return that the overall model pays for this is the time, right? So the cost overall, the cost of dropping out is that it takes more time to reach to somewhere, right? So question from Binta is, will they get paid? As per the current analogy, they are not getting paid. Okay, as per the current analogy, they're not getting paid. So now you will agree that yes, the company will actually perform better, right? So it's like many people send employees on unpaid vacation, right? Sometimes. So yes. So as per the analogy, the employees are not getting paid. Now you will agree that yes, the company will be more better, right? So right. So here probably the company would perform better. This is a very good example. So maybe the company would perform better. Why? Maybe let's say I and say Bintao are working in a team, and what we have done is we have figured out that um, that half of the work I can do, half of the work he could do, and therefore we are coming up with some kind of a result. Individually, we are not able to perform better. And someday, let's say I leave the company, and then Binta is not able to perform, or Binta has left the company, but and I'm not able to perform. So those kind of things would not happen if random dropout happens. So no single person will be responsible for, say, filling a coffee or cleaning the office or performing any other critical task. Instead, it will be everybody's duty. Therefore, if some people leave, the company will start working. It will continue to work. It won't happen that suddenly one person has disappeared, the entire company has gone down, has come down. So, therefore, the company would regularize because of 50% dropout, and hence, the company will be able to maybe able to perform better. So these expertise would have to be spread across many people. Employees would have to learn to cooperate with many of other workers. And this is an important part. So maybe because of this model, people will be more efficient. People will be more adaptive to others in the team. People would be more efficient because they know that they are the one who has to finish the work. So regularization might happen because of this. All right. So if you take this example, and probably that this was the example which was in mind of Geoffrey Hinton when he came up with this. So now, what would be the advantages of such system? The company would become much more resilient. If one person quits, there it would not make much of a difference. Not sure if this idea will work for companies, but it definitely works with neural networks. All right. So neurons trained with dropout cannot cannot co-adapt with their neighboring neurons. Okay. They have to be as useful as possible on their own. They also cannot rely excessively on just a few input neurons. They must pay attention. So if you are regularizing a neural networks with dropout, as in you're forcing on every iteration randomly 50% of the neurons are being dropped out, right? So what will happen is neurons will not co-adapt with their neighboring neurons, right? So you can think of maybe the brain works better when people, like a lot of creative people, uh, you know, are 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 kind of you know um, making themselves like sleep deprived or something like that. So half of the neurons are not working at that point of times. So a lot of creative artists did that earlier, that they kind of created all kinds of situations like being sleep deprived, or maybe using external stimulations. So in order to basically force their neurons to some of the part of their neurons to be kind of not working, and some of it is working. Maybe that's one of the reasons they mm, uh, were more creative. So essentially, the the neurons in this case of dropout, they will not kind of co-adapt with the neighboring neurons. Instead, they'll be more independent and will not kind of memorize, will not will not be a particular configuration is trying to fit. All right. So a point from Abhinav is, if they are not getting paid, then they will go to office without doing any kind of task. That's right. All right. So okay. So all right. So yes, actually, in one of earlier my company, the team I was running at TBITS Global, where I had done the hiring, from time to time, my team will actually take leaves, right? So I was kind of ready for they quitting, but they were not ready for me stepping out. All right. So from time to time, I started making one of my senior engineers take my job, as in my emails will be forwarded to him, and so on. So I did that very often. And that's kind of made it possible that things could run even without us. Okay. So that dropout idea is I kind of agree with it personally, that it would actually make people more efficient. And in the neurons case also is the same scenario. All right. So though the entire team was as in, since the team was taking leaves and they were so I was kind of ready, but they were not ready for me to take a vacation, right? Therefore it was important for me to take vacations and give somebody my shoes, my shoes to wear, and that was an important part. So it's equivalent of saying dropout. And so that's a justification for why dropout might work. So they can also rely on, so neurons will not to become dependent or correlated. They will also pay attention to other inputs from each other. As a result, they end up become less and less sensitive to slight changes to the inputs. Okay. In the end, we get a more robust network that generalize better. Most robust non-network that generalize better. Okay. So So to implement dropout using TensorFlow, just apply dropout function to the input layer and the output of every hidden layer. Okay. So what we need to do is we just need to implement dropout on the input layer as well as and the output layer of the every hidden layer. So during the training, dropout function randomly drops some items. After training, this function does nothing at all. It's also, please keep in mind that most of the regularization is for training. Most of the regularization is for training. We don't add those parts while predicting, while running on the validation. Okay. So, so here what we are doing is we are creating a dropout layer. We're creating a dropout layer here. Or you can say that we are passing the output of hidden layer through this function called dropout and giving it here. All right. So creating a one layer level in between. Let's follow the code here. Now let's take a look at actual code. Let me zoom it out. Okay. I hope it is clear. Now, so you have a reset graph here, and we are defining X and Y. So we have training equals this, and dropout is this. Okay. A question from Bintao is that there's a flag that we are defining here. Okay, there's a flag that we are defining with, it's a scalar value. Its default value is false. Why? Because we want to differentiate. We want to keep the difference between training and the validation. Okay. So since we only apply regularization at the time of training, therefore we cannot use the same neural network as such. We just have to avoid the dropout layer, dropout step while doing the actual prediction. Therefore, we are keeping a flag here that will be passing. So here we are saying that dropout rate is 0.5. Okay, x underscore drop is tf dot layers dropout. This is a standard tf TensorFlow function, and we are, for the input layer, we are creating the dropout. So for x is our input layer. So we are creating the x underscore drop. Now the next layer will get the x drop, not x. Okay. So next layer gives hidden one. And again, we are doing the same thing, hidden one underscore drop. Okay, and so on, right? So essentially, we are here in this layer. This is where we are dropping some of the outputs of the previous step. All right, and apply dropout in the second layer. So you can see hidden to here. Here we are not applying. Okay. Also notice third argument here. Training equals to training. So if we say false, then dropout will not apply. If we say true, then dropout will apply. So at the time of training, it will apply. Okay. Then we define usual cross entropy, then loss function, the usual one. Rest of the one remains the way we define. So here we are using the momentum optimizer. We could use adaptive or Adam, and that's it. So let me go back up and then start. So we defined inputs and Y the outputs labels. Then we created all the hidden layers with the dropout. Then we computed loss and then created the training part, and then we did the validation part, validation node. And once that's done, then we run it. We run it usual way by using session.run and computing the accuracy. So here it is starting to run. All right. So a question from Vidya is that I wonder whether some information is missed out by dropout strategy. So it seems so in the first go, but if you think of it, it is not, because every iteration randomly some of the neural network, some of the neurons are being dropped. And those ones will be reutilized earlier. Maybe at this stage, let's say here, X drop, right? We are we are dropping some of X, correct? But maybe on the first step, let's say out of ABC, A and B got dropped, then B and C and A and B. So after a runtime, after some time, you'll realize that all of the inputs have been used. All of the inputs have been used. Okay. So maybe then there is a chance of it underfitting. So what you do is you increase the total number of neurons and do the dropout as 50%. Okay. A question is, what is in top K? Remember our discussion last time? What we did was when we are saying in top one here, right? In top one, we are saying if actual prediction is in the predictions top one of the prediction. If we said, okay, even if our outcome is in top two, we are okay. Here we are saying y should be the most probable out of the logits. So logits is nothing but an array of probabilities, right? Array of probabilities. And basically here it means that y should be in the top. That's what it is. All right. So this is the kind of accuracy we are having here. Okay. How many layers are there? There are two hidden layers. That's all. Okay, we could define. All right. So so a question is, how about in top K and logits Y in at 2? So let me just show you this part. Okay, let me see if I could. Okay, let me try this. I just want to give it a try. Okay, so here what we are saying, so training is going to be false, and we are not calling this. Let me just show you what it means. So first of all, let's take a look at logits. Okay, and here, okay, so what does it say? No. We'll see this later. Okay, so what I wanted to show you was, okay, basically some variables need to be defined at this point. All right, so in top K basically gives you the, if you have to say, let's say this is the probability, right? And how should I say? Okay, so we get the probabilities of okay, so I'll explain again. Let me go down here. Okay, it has finished. Let me try again if it works.
Okay, what was the name of this? No. All right, we will, yeah, we will see that later. Okay, not logics. I think we can just compute the, here, where did it go? All right, all right. So yeah, so basically, let me rephrase what it means. It means, what it means is that given given what is logits? Logits are nothing but the outcome of the last layer, right? The outcome of the last layer. So there, what we are comparing is, we are saying that this is our y. Is this one in the top most probable? Okay, y1, right? Had this been 2, even if y comes second in the actual one, it's completely okay. All right. If we say 3, if y is any of the top 3 of the logits, then this is completely okay. All right. This is completely okay. And yeah, that's what it is doing. Okay. The in top k is doing that. So you should try this function. So you can try it separately also. Okay. So essentially it is finding the top n value. So says whether the targets are in top k predictions. Okay. Targets are in top k predictions. K is the one that you are passing. All right. So that's what I, yeah. All right. You can remove this. All right. So this is how we did the dropout on our code. All right. Now moving ahead. Now, if you observe the model is overfitting, then decrease the dropout rate. Increase the dropout rate, not decrease, meaning the probability should be increased, the value that you're passing. Else, if the model is underfitting, then decrease the dropout rate. It can also help to increase the dropout rate for larger layers and reduce it for smaller ones. Okay, so the general thumb rule is that let's say your model is giving good enough results, and but it is also starting to overfit. So increase the number of neurons in the hidden layers, and and then you start the dropout. So that would actually make more sense. Please note that dropout does tend to slow down convergence, but it results in a much better model when tuned properly. It is worth the extra time. Okay. Now, the next important part that we had discussed part of it earlier is called data augmentation. All right. So data augmentation consists of generating new training instances from the existing ones. So a very common question that you will face is that, hey, we have to do this complex task, but we don't have data. Let's say you're supposed to do image recognition on flowers, but you don't have sufficient data. In that case, what do you do? Other than other than taking a pre-trained model and enhancing it further, you could also do something called data augmentation. So generating new training instances from existing ones, thereby increasing the size of the training data. So let's take an example. Let's say we have to train a model to classify the pictures of mushrooms. Okay, then we can slightly shift, rotate, and resize every picture in the training set and add the resulting picture to the training set. So basically, from the same training set, we can generate much more data. Okay,
So let's take a case. Let's say there is a picture. There is only single picture provided to us, and with the label saying this is a mushroom. Okay, this is what is provided. So all we do in this such cases is generate as many pictures from it. Here we are tilting it a bit. Here we are shifting a window a bit. Here we are changing the color a bit, and here we are again tilting it to the left. And then here we are zooming it a bit and cropping it a bit and so on. So you can see that there are many things that we could do on the same image. So from some single record, we could generate like 50 records by slightly shifting by 1 pixel, rotating by another pixel, and so on, changing the color, changing the gradient, and so on. So this way, by augmenting the same data with slight variations, we could do many things here. Okay, we could generate more data. So the trick is to generate realistic training instances. A human should not be able to tell which instance was generated and which ones were not. Moreover, the modifications we apply should be trainable. Modification that we apply should be learnable. Okay, so So basically, these newly added pictures forces the model to be more tolerant to position, orientation, and so on. Okay, what does it mean by modifications to be learnable? Meaning these modifications, we want them to learn. We want our model to learn that actual image in actual one, the the image could be the image could be tilted a bit, image could be in a different color, image could be in a different resolution, and so on. So our model will become tolerant to various variations. Okay, this actually improves our overall model's performance. If you want the model to be more tolerant to lighting conditions, we can also generate images with various contrasts and add them to the training set. It is preferable to generate new images on the fly during training rather than wasting storage space and network bandwidth. So TensorFlow offers many functions for image manipulations, such as transposing, rotating, resizing, flipping, cropping, adjusting the brightness, contrast, saturation, and hue. So there are many functions provided by TensorFlow, and of course you can use any other library as well. These operations makes it easy to implement data augmentation for image datasets. All right. So that was pretty much about data augmentation. I hope data augmentation is clear to everyone. All right. So Balaji, Vidya, James, Pawan, Pratik, and Shahrukh, are you still with me? All right. So when we are going to the next chapter called convolutional neural network, we will learn all of these parts. We will apply these techniques and in a project or two, and we'll experiment with the augmentation and regularization even more. Okay. So all right. Now the practical guidelines. So whatever we have learned in this chapter, it's actually can be summarized in this way. Okay, we have talked about many things in this chapter, and the common question comes on which one to use. The configuration shown below works fine in most cases. So we had all kinds of problems overfitting, like overfitting, gradient, the vanishing gradients, the speed being slow, and so on. So the general guidelines are for initializing the weights, we use HE initialization. right? Remember the he initialization in which we had square root of 2 divided by, if we are computing the standard deviation is basically square root of 2 divided by total number of inputs and outputs. While the min max, the range of min max was between the r and minus r, and r was square root of 6 divided by number of inputs and outputs. Remember? So that was our he initialization. So for initialization, you use the he initialization. Activation functions, you use the ELU, the exponential linear unit. And for normalization, you use the batch normalization. Regularization, use dropout, not the one that we L1 and L2 that we studied. Optimizer, we use Adam. And when we are using Adam, we don't need any learning schedule. Okay. So basically, other than the other than the uh, basically these are the various these are the conclusion of whatever we learned. Even though the chapter might look really long, we have gone through so many things. the the purpose of this session was not to just tell you that this is what you should use. Instead, the purpose was to give you an idea why these things have been designed in this way. These things, why we come to a particular conclusion. That was the purpose. So that you should be able to optimize your algorithm. And you will notice that this is very common. It's not very uncommon to optimize each of these parts. And you can see there's a lot of scope for research. There's a lot of scope for experimentation. And there's a lot of scope to coming up with your own optimizers or your own initialization techniques. And that happen all the while. That happen all the while. You'll notice that every year, every month, there's a new technique amongst all these 6, 7, these new techniques. Like for example, the 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 Adam optimizer came into picture in 2015. Okay, so and it's basically a combination of two different techniques, and that's how it worked. All right, so these are the practical guidelines, but it's important to know why we choose these guidelines and how these work, so that if something is going wrong, you would know why it's going wrong. Because in case of machine learning, there are going to be various levels of expertise that you will gather. Initially, you will just use the API, then you will use somebody else's model, and you will use the out-of-the-box things. Then you will start to optimize and learn how to overfit and learn how to avoid overfitting and underfitting and so on. So always look for pre-trained model if possible. If not, then try, if the data is less, try the data augmentation. And the default configuration, which we have shown in the last slide, may be tweaked as per the problem statement. If the training data is too small, then implement data augmentation. If you can't find a good learning rate, then try adding learning schedules. Okay. And so the exponential decay is a good learning schedule, the last one. If we need a lightning fast model at runtime, then drop the batch normalization and replace ELU with ReLU. Okay, so if you want to do real time, so based on the problem statement, you might have to change the strategies. All right, so that's pretty much for the training model. There's one more one. If we need a sparse model, add some L1 regularization. With these regularization, we can train deep neural network. But if we use a single machine, then it may take days or months for training to complete. So be patient. As the train the model across the servers and GPUs. So that's pretty much for the training model. So we have learned quite a few things as part of this. We learned vanishing gradient, initialization of weights, activation functions, and batch normalization. Then we talked about gradient clipping and reusing pre-trained layers. And then we also learned about various optimizers and regularization. Okay, so and the data augmentation. So we are going to start with the convolutional network tomorrow. So we're going to start with convolutional neural network from tomorrow. All right. So thank you, everyone. I look forward to see you tomorrow at the same time. Network and nets are same thing. Okay. So CNN, convolutional neural nets, or network, it's the same thing. All right. Thank you, everyone. I look forward to see you all tomorrow. Yes. Min-max normalization we talked about there when we talked about initialization. Okay. Min-max initialization. Okay. So we can take up this question tomorrow, Binta. All right. So that's pretty much for today. Okay. Great. Great. I look forward to see you all of you tomorrow. Come over to the discussion forum. We can have more questions. Bye bye. Have a good day. All right. Thank you.